realize I put the display down low because I wanted to save batteries. I can't hardly see it. Okay. So this is an aldehyde, and it is propanol. Al. So we're bringing the Al from the aldehyde. The second one, butanone. And it is what? Aldehyde or ketone? Ketone. And so we're taking that ONE, butanone. So we're taking the ONE out of the word ketone and adding it as the suffix. Okay, these are the things that the IUPAC system is doing that is very helpful. Okay, this is what makes this manageable. Is we've got BUT that tells us 4 carbons. We have ONE that tells us a ketone. Now, what is a ketone? It is a carbon-oxygen double bond along the chain somewhere, not on the end. Okay, the next one. 1, 2, 3, 4, 5, 6, 7.
3, 4.
Okay, heptanone. I like that so far. But that's not enough. 4, heptanone. Okay? This one has to have a number. Once you get past butanone, you have to have a number. Why? Because butanone, it has to be on the second carbon. There's no other place. There's no middle carbon. There is a carbon that is one in from the end on either end. So no matter where you put the carbon-oxygen double bond, it's going to be on the second carbon. So if you put 2-butanone, I don't know if I'd count it off, but I would scratch that out and just say it's not necessary. But here, if you did not put a 4, I would count off for it, because just to say heptanone, it could be here, it could be here, or it could be here. So there is a 2-heptanone, a 3-heptanone, and a 4-heptanone. This one happens to be 4-heptanone.
So sorry, but why wouldn't you put 2-butanone?
Well, if we had this molecule, I'll just put it the way they have it, CH2, CH3. If we had a CH3 here. Okay, can you see that is superimposable on that? It's the same.
Oh, okay.
So
Because if I flip it around, it's the same thing. Okay.
yeah, it's the same molecule. So why do we need numbers in there? Well, when it is unique. Now let's skip that one for a second and go up there.
Mr. Rion, I was going to ask, could there be a 5-heptanone?
Good question. Could there be a 5-heptanone?
Yes.
No.
Oh, why?
If it was right there, it'd be 1, 2, 3 heptanone.
Oh.
It would not be 5. So there's no 5-heptanone. There's only a 2, a 3, or a 4. Those are the only 3 heptanones that are unique heptanones. Got it? You don't just keep counting all the way across and come over to here and get a 6-heptanone. That is 2-heptanone. Okay? Confusing, huh? All right? Okay, what is the bottom line? If the 2 molecules are superimposable on one another, they are identical. And they don't need a unique name. They don't need 2 names if they're the same chemical. They only need another name when they are really a unique molecule. Okay, now this one, I think I do go over this one in the lecture. Here we got an aldehyde. Oh, we didn't do that one. What is that one? It's an aldehyde. What's the name? Butanol. Okay? Okay, now over here we have an aldehyde and an alcohol. So we're going to treat that as a substituent. And so let's see, how many carbons are there? 5. So it's going to be pentanal. So we're gonna stick with that as the parent name. It's a pentanal. It's going to be 2-methyl. I should have planned ahead here. So it's going to be 2-methyl pentanal. And we got a hydroxy group here. So 3-hydroxy, 2-methyl pentanal. So we can't call it, we can't put an OL and an AL in the parent name together. I mean, we could do that, but that's not what IUPAC does. It fixes on the aldehyde. The aldehyde is not going to be a substituent. It's on the chain, and we're going to revert to using the looking at the OH group now as a substituent. And let me just use this to point out again that the way we'll construct the name is in 3 parts. The parent name is the major part at the end. Any alkyl groups, methyls, isopropyls, ethyls, butyls, whatever, will be alphabetized here in the midsection of the name. And then any chloros, bromos, hydroxys, whatever, will go at the front in this miscellaneous.
Does the alphabetical not?
I wouldn't worry about it. I don't think.
You could have like a 3-hydroxy 2-ethyl, but like ethyl is before H.
No, you're not going to alphabetize. You'll alphabetize alkyl groups in this section.
So if it was like 3-hydroxy, 2-ethyl, 2-methyl.
Right. If there was an ethyl group here, you would be 2-ethyl, 2-methyl pentanal. Okay. Now let me just back up a couple slides here. All right, here is a good slide for you to star. These are basically the molecules that you should have 3x5 cards on for chapter 13. Because what you can see here are IUPAC names, common names. Formaldehyde. How many of you have heard of formaldehyde? How many of you have heard of methanol? We don't call it methanol. That's its official IUPAC name. But it is most commonly referred to as formaldehyde. Okay, so you need to know that. You need to know what formaldehyde is. It's a single carbon aldehyde. Acetaldehyde, that's a very common compound. Ethanol, and it's most often referred to as acetaldehyde. Okay, so you need to know that name. These are the really critical ones. Propionaldehyde might show up, butyraldehyde. Okay, benzaldehyde. Okay, it's the same name. The common name was grandfathered into the IUPAC system, so it didn't get a new name. They just used it. But you should really know and be able to draw benzaldehyde. You're going to have a series of aromatic, 6-membered aromatic rings, starting with benzene and toluene and phenol and now benzaldehyde. They all have some functional group on a benzene ring. And there'll be 2 or 3 more to add to it, but this is part of the collection. Benzaldehyde. Then we've got propanone, which is almost never called propanone. How many of you heard of acetone? Okay, acetone, one of the most common solvents in a chemical lab that's dealing with any organics. There's DI water bottles and acetone bottles over in the lab. And what is acetone? It is the simplest ketone. 3 carbons long with carbonyl in the middle. It's a ketone. Okay, this one actually has 3 names. Butanone, methyl ethyl ketone, or MEK. MEK. You can walk into labs, you can walk into a research lab, and there'll be bottles of MEK on the desktops, on the benches. MEK. So chemists look at that and go, oh, that's methyl ethyl ketone. And notice that they don't alphabetize it correctly. Okay, it's not ethyl methyl ketone, it's methyl ethyl ketone. Common name. It's kind of like our English language, all right? We've got some weird words that pop up and say, why does it mean that in this case? Cyclohexanone. Those are probably, I'm going to just asterisk some of them. I mean, you should know them all, but if you are going for percentages, I'll pick on those. All right? And what you're going to see is that form, we're going to move on ahead here, when you see form, even in a common name, it's a 1-carbon compound. And when you see acet, it's a 2-carbon compound. We're going to get into acetic acid. It's 2 carbons long. Formic acid. So those actual prefixes, even though they're common names, are going to be reoccurring in other functional groups.
You said acet is
2 carbons. So acetic acid, that'll be in chapter 14. All right. So now I'm going to get through to try to complete these reactions. Let's see, where were we? Okay, you heard me. I think if you listen to the tape, you heard me talk about urea formaldehyde foams, right? And the way that ruined hundreds, thousands of homes by trying to insulate them with urea formaldehyde foam. Formaldehyde is a carcinogen. And if you want to talk about sick buildings, I mean buildings that actually make you sick because of some of the construction materials that were used, that's an example right there. Pardon me?
Is that like asbestos?
It's not as bad as asbestos, I don't think, but I mean it's a carcinogen. Asbestos is just really ruins the lungs. So it's different, you know, it works differently, but formaldehyde causes cancer, so. All right, so I think there are just some slides here of just some common, you know, vanilla, you can see the aldehyde, the bunch of functional groups in there. All right. Caffeine is going to, so cinnamon aldehyde, lemongrass. Now these are naturally occurring compounds, and you can start seeing the different organic functional groups that are showing up. We've got double bonds in here. We've got an aldehyde. This is lemongrass. Mushrooms is 2-octanone, so it's a ketone. Cinnamon aldehyde, you've got the benzene ring, a double bond, and an aldehyde. Cinnamon aldehyde. So they could look kind of scary, but they're natural and actually can be not scary, but I mean they kind of look like synthetic chemicals, but they're not. These are naturally occurring chemicals, and to some extent have beneficial effects. And then of course our favorite, caffeine. Not everybody's. It seems like it is. I mean, it's hard not to go somewhere, not find a coffee shop, or 4, or 8, or 10. All right. So chemical reactions. Let's see. We got to make these a little bit bigger. Be nice to make them even a little bit bigger than this. Okay, I'm going to whisk through this slide because you've already been exposed to this reaction. It's under the heading of preparing aldehydes and ketones. And what's a way to prepare an aldehyde? Well, oxidize a primary alcohol. Primary alcohol will oxidize to an aldehyde. We learned this in chapter 12 of the reactions of alcohols. So you can take one butanol and make butanal or butylaldehyde. Secondary alcohol. Here's a secondary one. I kind of wish this was drawn here and you could see the OH up here. I mean, if you bend this down and that up there, you can see this OH is on the second carbon. 1, 2, 3, 4, 5, 6. And you end up with the carbonyl on the second carbon. 1, 2. All right, so this is on that carbon right there. I don't know why they twist it around like that, but see, I blame it on somebody else. It's my slide, but I blame it on somebody else. This is a ketone. So a secondary alcohol will oxidize to form a ketone. Like I said, you already know that. All right, and the next slide is going to, and the tertiary, no reaction. Okay? This is old stuff. This was actually on the exam. Okay, now we're going to go one more step with this primary alcohol in terms of reactions. Because a primary alcohol can oxidize to form an aldehyde, and it can go one more step to form a carboxylic acid. An aldehyde can oxidize on further to a carboxylic acid. And we might as well go back to that last slide to show that. So here the butanol forms butanol, one butanol forms butanal, and it can oxidize further, and it would form butanoic acid. Don't worry about the name. That comes in chapter 14, naming these. But that is the acid. That's a carboxylic acid. Aldehyde, carboxylic acid. We keep the carbon-oxygen double bond, we add another oxygen. That's oxidation. Addition of oxygen, loss of hydrogen. All right, and this is just another example. Here's ethanol, and it can oxidize further to acetic acid, or the acetate anion. Acetic acid would just be, you'd have the OH there. This can get a little bit confusing. That's the carboxylic acid. That is just it when this acidic proton has come off of it, gone into solution, and leaves behind this anion, but it allows the release of a proton, an H+, into the water. That's what makes it acidic. You take ethanol, alcohol, make a mixed drink with water and alcohol, it doesn't change the pH of the water. The hydrogen doesn't come off of the ethanol. This hydrogen, no, not that hydrogen. If you had ethanol, this hydrogen does not dissolve, doesn't ionize in the water and make it acidic. So we don't think of ethanol as an acid. Ethanol is not an acid. pH 7, mixed drink. But you take acetic acid and put it in water, and you get that sharp taste of vinegar. It is lowered the pH a fair amount, pH 3. It's a weak acid, but it is an acid. Okay, okay, this looks like a complicated reaction. This is one in the 1107 lab you will come across. we will try to do this reaction. A Tollens test is a test designed to distinguish between an aldehyde and a ketone. So if you have something, you go, this has got a carbon-oxygen double bond on it, but I don't know whether it's an aldehyde or a ketone. You might do the Tollens test. And what the Tollens test does, you start out with your aldehyde, and you start out with a silver ammonia complex. That's the Tollens reagent right there. This is your Tollens reagent. So let's not get all bogged down in all this stuff, but what's changing? The silver ion, Ag plus 1 ion, is becoming metallic silver. And the aldehyde is oxidizing to a carboxylate. It's being oxidized. The silver is being reduced. And what do you see on a positive Tollens test? The inside of the glass test tube or flask, whatever you're doing in it, turns into a mirror. The silver actually plates out on the glass, and you form a mirror. And that is a positive indication that an aldehyde was present. That's a Tollens test. It's kind of a neat test when it works. It's a little bit complicated. It's got to be very high pH. The Tollens reagent has to be fresh and right. So it's not like the bromine test on double bonds that's pretty ironclad and behaves the same way all the time. This one is a delicate test, but done correctly, it can distinguish an aldehyde from a ketone. That's a Tollens test. Okay, this is Benedict's test. This will come up a couple of times. Here, I think for the first time, and then again in chapter 16, chapter 16, when we study sugars. We're gonna be exposed to this again. The Benedict's test. It is a very simple, and it's a basis for a very simple urine analysis to see if an individual is passing sugar into their urine, so that sugar is actually being excreted through the kidneys, which is not normal. The body retains sugar, does something with it, burns it or stores it, but doesn't excrete it. So if it is being excreted, then there's something wrong with the sugar balance and onset of diabetes and things of that nature. So this is a very simple test. And what it is doing, here's sugar, here's glucose. Well, what is glucose? Well, it's got a bunch of stuff on it, but it is an aldehyde. Glucose is actually an aldehyde. And you can take a copper, which would be the Benedict's reagent, and react it with glucose, and it will oxidize the aldehyde, and it will reduce the copper. That's what a lot of these tests are doing. They're playing on color changes that these transition metals go through when they change their oxidation state. Because when one molecule is being oxidized, something else has to be reduced. And so you're reducing the copper, and it changes colors from blue to red. Copper plus 2 is blue, copper plus 1 is red. And you get this color change. So let's take a peek at it here. So here is an example. So let's say you had, let's see, left panel, Benedict. So here we got 0.5% glucose and 2% glucose. And over here we got 0.5% glucose and 2% glucose. So here is beginning, here's the end of the test. So what did we do? We took half of this Benedict's reagent and poured it into this test tube, and the other half of it and poured it into that test tube. And what is this here? This is your copper plus 2 ion that is blue. And what do you have over here? You got your copper plus 1 ion that is red. So what do we have here in the middle? Well, we didn't have as much glucose over here to react with that Benedict's reagent. And so there is some of the blue, so there's a mixture of blue copper 2 and red copper 1 in here. You follow that? We didn't get the complete reaction of the Benedict's reagent. Got partial reaction. But we did get a color change. We did get a color change. We'd say, oh, there's some glucose in there. And this is really the urine analysis. They can have sticks. They put it down into the urine sample, and it changes different colors. And they can actually say, there's a lot of glucose being eliminated from the body, or there's only a little bit. It can actually be somewhat instructive of whether it's a severe situation or not, just by color. Are you following that? We've got a little bit of both. We got a little bit of this and that in here, because there wasn't enough. You see, there's only one quarter the amount of glucose in here as there is in here. This is 4 times more concentrated. So it overwhelmed the Benedict's reagent and reduced all of the copper, and it turned red. All right, that's Benedict's test, the Benedict's test. And a copper plus 2 reagent is the basis of the Benedict's test. Well, let's see. I don't think I would have you write out a Benedict's reaction, but you should know what the colors are of the original reagent and what a red color would indicate and that sort of thing. So yeah, you should be aware of the basic concept. But to actually say, draw out the Benedict's test, I don't think we would go into that. Okay, now it would be nice to have a copy of my slides in front of me. I think we're going to segue now on into reduction of aldehydes and ketones. So that's why this slide's coming back up again. We concentrated on this when we talked about the oxidation of alcohols to aldehydes and ketones. That oxidation is the gaining of oxygen, the loss of the loss of hydrogen, or either one of those. Coming back this way, reduction is the loss of oxygen or gaining hydrogen. Gaining hydrogen. So grab onto that. And we're going to talk about hydrogenating, the hydrogenation of aldehydes and ketones. And what is hydrogenation? It is adding hydrogen to a molecule. 2 hydrogens. Because hydrogen is H2. You're adding 2 hydrogens to a molecule, you're reducing it. So what we just got done saying, reduction is either the loss of oxygen or the gaining of hydrogen. So hydrogenation, by definition, is reduction. They're synonyms almost for one another. Well, there's 2 reactions going here. We've got an aldehyde down here, and we have a ketone up here, and that's probably a little too busy. So let's focus in on this one right here. Let's move on down. Okay, so there's two reactions there. That can be confusing. In other words, this middle part is to be right in the middle of, or it should be in front of each one of them. So let's look at this one. Here's our aldehyde, and we're adding hydrogen, and we've got some sort of a catalyst. It could be platinum, palladium, or nickel. It's not all three of those. Any one of those three. And these catalysts are like parts per million. And you are going to get, now here's what's going to happen. I'm going to expand this right here. Here's our aldehyde. Think of our aldehyde right there. Here's our hydrogen. And this should look familiar. When we talked about the hydrogenation of an alkene, we talked about adding hydrogen to a carbon-carbon double bond. Now what are we doing? We're adding hydrogen to a carbon-oxygen double bond. And so each one of these atoms gets a hydrogen. And we eliminate that double bond right there. We keep that one bond, but we eliminate that bond. So what happens? We get an OH there, and we get an H there.
Can we get water and alcohol?
No, we don't get water. We get an alcohol. Okay? We're not getting any water. This is hydrogen. That H is going on there, and this H is going on there. So we get an alcohol. The reduction of an aldehyde produces an alcohol. And not only does it produce an alcohol, it produces a primary alcohol, an aldehyde. So we go from an aldehyde plus hydrogen forms a primary alcohol.
So you will never get
Ketone?
a major,
You never get a what? A major or minor product? No. No, this is the only product. No, there's no major or minor rule here. An aldehyde will produce a primary alcohol. And why is that? The oxygen on an aldehyde is on the end carbon. It's not moving. There's nothing about that oxygen that moves in this reaction. It stays on the carbon it started with. It started on the end. Now we have that oxygen still on the end, but we've added a hydrogen to it, which is converted into an alcohol. So wherever the oxygen is doesn't move. Keep that in mind. You're just adding hydrogen. One hydrogen to each of two atoms. One happens to be an oxygen, one's a carbon. This is very analogous to hydrogenating an alkene, but that doesn't produce an alcohol, that produces an alkane. This produces an alcohol, yes.
So then that would be attached, the OH, CH2, would then be attached to a parent chain?
Yeah, I'm just, all I'm doing right here is just focusing in on that right there. All right, so this is the completed reaction. All right, so this is what this looks like on this end. I've just got a line there. That could be any aldehyde. Any aldehyde is going to end up looking like this. If it was 2 carbons long, it'd be 2 carbons long and look like this on the end. Okay, now let's take a peek up here. Again, we're dealing with a ketone that's 4 carbons long. So here's a ketone that is 4 carbons long, plus hydrogen plus some sort of catalyst.
And then this would create a major and minor because it's in the middle.
No, there's going to be only one product here. There's not going to be a major or minor.
Would it still be considered a minor though? I mean, like technically speaking, it's minor because it's on the end.
Well, okay, what may be confusing you here, like I said, this is too busy of a slide. There are two reactions here. The aldehyde produces always a primary alcohol. Only one product, primary alcohol. The ketone always produces a secondary alcohol. There's no way to get a secondary alcohol from an aldehyde.
Oh, I know that. I'm just saying, technically speaking, it would be considered. Like,
It's the only product. So that's why we don't use the word major or minor. It's the only.
So the
It would be the major. I mean, it is a major because there's 100% of it is going to be that product. Yes, another question?
So the reduction, say the thing about the ketone again.
Okay, now,
I understand that the reduction of an aldehyde produces a primary alcohol always and forever.
okay, so here, class, let's you answer this question. We're going to hydrogenate a ketone. So it's going to produce an alcohol. What kind of alcohol?
A secondary alcohol. Okay.
And why does it have to be a secondary? Because that oxygen isn't going anywhere. The oxygen, we're going to get rid of one bond, but the oxygen is still going to remain attached to that second carbon, and we're going to get a hydrogen on the other side of that second carbon. So we see what we're doing here? Here's our hydrogen. One hydrogen is going there, and one hydrogen is going on this carbon. There's our hydrogen. Right there. And we produce, so a ketone plus hydrogen forms a secondary alcohol. All right. Got it? Let me see, where are we? Oh, there's a couple more slides. Let's see if there's another major reaction that we have to do. Oh, the hemiacetal reaction. Gunther. Hemiacetals. I don't think we can. I'll start out with the hemiacetal. I'm not going to dismiss you yet. I want to at least mention this project that you're doing. I tried to print something off. Let me give you something to think about. Hopefully there's someone from every team here. In some cases, maybe your whole team is here. I think I will. All right, we'll pick up with hemiacetal on Wednesday and then dive into chapter 14. So I will